Hello students, I am Dr. Rajaram Dhok from Savitribai Phule Pune University affiliated Agricultural Development Trust Shardabai Pawar Mahila College Sharda Nagar Baramati. Let's start. We learn about the crystal field theory, and in this crystal field theory in the 7th lecture we discuss about the factors affecting the magnitude of 10D or delta O. So 10 dq means the energy of difference between the T2G and EG. This value or 10 dq value changes in different complexes. How that changes? What is the magnitude of that? And which different factors are responsible for that? For that purpose, we see the different factors responsible for the changing the magnitude of 10 dq. So, in the factors affecting the magnitude of 10 dq, in the octahedral complexes, there are three main factors, and in that, first factor is nature of ligand. Second factor is charge on the metal ion. And third factor is the row in which the transition metal is placed. In this way, there are three main factors. First is ligand, second is the metal, and third is position of metal in transition series. So we see this all the three factors one by one in detail by using the suitable examples. And from that, we can see that how that 10 dq values are changed. So firstly, we see the nature of ligand. So in the ligand, there are various types of ligand, and that ligands are arranged in spectrochemical series on the splitting ability of that ligand. Here we take one example. From that example, we get idea about that ligand and how absorption bands or delta energy changes. So we take the chromium metal and various ligands like chloro, aquo, amine and cyano, and its octahedral complexes are prepared. So CrCl6 3 minus, its delta energy is 163 kilojoules mole raised to minus 1. In CrH2O6 3 plus, delta O value is 213. In CrNH3 3 plus, delta O value is 259. In CrCN6 3 minus, delta O value is 340. Now, when we observe these values and these chromium compounds with different ligands, then we can easily explain that the ligand which is higher position in spectrochemical series, that ligands form stronger complexes and its delta values are higher. So you see here the CrCN6 values are 314, and it is near about double than the values of the chloro ligand, because chloro has lower position in the spectrochemical series and cyanide has topper position in the spectrochemical series. So simply we can say that here if ligands are higher position in spectrochemical series, then it forms strong complexes than the other ligand which have lower position in spectrochemical series. Now we see the nature of ligand. In the nature of ligand, the values of delta O that increases with increasing the strength of the ligand. So just we have seen that all the points. Then charge on the metal ion. So metal ions have different charges depending upon the how many electrons are donated. And when charge on the metal ion is changed, then its size is also changed. So in the crystal field theory, here this crystal field theory is based on the electrostatic model, electrostatic force of attraction. So charge on the metal ion has direct effect on the magnitude of 10D. So this charge is mainly affected on the size. It also effect on the magnitude of 10D. And so we see this metal ion, how affects on the magnitude of 10 dq, and for that purpose we see the different charges on the cation of the same metal. Mean there is same metal, and in that same metal there are different charges. Then in that case, how that affects on the magnitude of 10 dq. So in this case we take the example of CrH2O6 2 plus. It shows 10 dq value 39.7 kilocalories per mole. And for the CrH2O6 3 plus, 10 dq value is 50.94 kilocalories mole raised to minus 1. So from this example, here you see that CrH2O6 2 plus and CrH2O6 3 plus. In both the complexes, metal is same, ligand is same. But in the second example, chromium has plus 3 oxidation state. In first example, chromium has plus 2 oxidation state. So when there is higher charge on the metal, that higher charge can polarizes the ligand more effectively. And so the ligands can approach more closely to that metal ions, and that results in the greater splitting of that d orbital, and there is formation of higher energy. So simply we say that the metal which have more charge, it forms strong complexes than the others which have lower charges. Then we take second point in this case, that different charges on the cation of different metals. So when two different cations with same electronic configuration and same geometry of the complex we considered here. So it observed that the cations with higher charge have higher delta values, and they are more stronger complexes. So we take here one example, P2 plus and chromium 3 plus. So in Fe2 plus ion, we take example FeH2O6 2 plus. Its delta value is 12460 centimeter raised to minus 1. And in Cr3 plus, here example CrH2O6 3 plus, delta value is 17400 centimeter raised to minus 1. So in this case, here higher charge on the chromium ion than the vanadium plus 2 ion, that can polarize the ligand more effectively, and so the ligands can approach more closely to the chromium 3 plus, and that can result in the greater splitting of that metal, and it forms stronger complexes. And so here chromium plus 3 forms stronger complexes than vanadium 2 plus, which have here same or metals, but here different metals and different charges. Then third case, same charge on cation with different electronic configuration. So in this type, the values decreases with increase of d electron. Here values of delta O decreases when there is increase in the d electron. So here we take the D7 and D8 case. So in D7 case, here cobalt complex COH2O6 2 plus and NiH2O6 2 plus. When we calculate the D case, then in first example D7 case and second example D8 case. In this case, here second example has 8500 centimeter raised to minus 1 delta O value, and for the D7 case 9300 centimeter raised to minus 1. Means here values decreases when there is increase of d electron. So in this way there are different factors in case of the metal, that can affect on the magnitude of 10 dq. Now, the third factor, that the transition metal is taken from different transition series. So what is the position of that transition metal in that transition series? And for that purpose, we take the example from different transition series, that is first row element or first transition series element, second transition element, and third transition. So from first, we take the CO NH3 3 plus, RH NH3 3 plus, and IR NH3 3 plus. We see its delta O value. So delta O value in centimeter raised to -1 and delta O in kilojoules molecule raised to mole raised to -1, that is given. So we consider 1, that is kilojoules mole raised to -1. So in cobalt complex, delta O value is 275. In rhodium complex, delta O value is 406. In iridium complex, which is third transition series element, that is 490. Means here from these values we observe that second transition element have higher value than first transition element. Again, third transition element or third transition metal have values more than the second and already first. So here we can observe that values of delta O increases when we go from the first transition series to second transition series and second transition series to third transition series. If we see the actual values, then d orbital splitting that can be observed in order that 3d is less than 4d and 4d is less than 5d, or we simply say that 5d is greater than 4d, 4d is greater than 3d. Means simply we say that from first transition series to third transition series, delta O value increases. How many that increases? So we observe that in case of the first transition series, that is 3D to 4D, near about 40 to 50% energy is more, or it increases. And from 4D to 5D, near about 20 to 30% energy or delta O values are higher. Means simply we say that third transition series energy is near about double the first transition series metal. This is the approximately. So these are observed the different changes in the transition metal complexes. Now we see that crystal field theory and magnetic properties of metal complexes. So this crystal field theory explains also the magnetic properties of that transition metal complexes. So in the transition metal complexes, the electron pairing energies are observed. Some electrons are unpaired, and this electron pairing energy and free electrons, it determines the magnetic property. If the crystal field is strong, then in that case maximum electron pairing is observed, or electron pairing takes place, and in that cases the properties shown by that compounds are diamagnetic. For example, we take the FeCN6 4 minus ion. In this FeCN6 4 minus ions, maximum electrons are paired, and so it shows less number of unpaired electron, or it shows diamagnetic properties. In case of the weak field complexes, electron pairing is generally not observed, or firstly electrons are single field. So in that case no electron pairing takes place, and the complex shows generally paramagnetic properties. And for that purpose, we take the example of FeF6, similar example to the FeCN6, only ligands are changed, metal is same, total number of coordination number is also same, And so we take the Fe F6 4 minus ions. It contains 4 unpaired electrons. So simply we say that in the second and third transition series, spin pairing will be much more. Or in the second and third transition series, maximum electrons are paired. And because of that, 10 dq is 50 to 100% larger than the first transition series element. And in that, spin pairing energy becomes less. So heavier transition metal that forms low spin complexes. So in case of the second transition series, third transition series, unpaired electron numbers are less. So that is called as low spin complexes. So with the help of this crystal field theory, we can find out number of unpaired electrons and magnetic properties of that complex. So we can calculate these magnetic properties or magnetic moment mu of that complex, and for that purpose spin only formula is used. So what is that spin only formula? That spin only formula is mu is equal to under root n into n plus 2, and that magnetic moment is measured in the unit Bm, that is the Bohr magneton. So by using that formula, we can find out the magnetic property or magnetic moment. So here n means number of unpaired electron or number of spins. So when we know the unpaired electron, how many unpaired electron present in the compound, then by adding the value of n, we can find out the mu or magnetic moment.